In this video, I'm going to continue talking about the control system performance. So this is the part 2 for the control system performance. We'll focus on the second order system. Now, in the previous video, I talked about the control system performance for first order system, which is given by 1 over s plus 1 over tau. So this is the system we're talking about. Now here we talk about a different one, which is Wn squared divided by s squared plus 2 theta Wns plus Wn squared. So this structure, you in your actual system you can have a little bit different. You could have something like you don't have Wn squared, you have a 1, which is okay because you can scale it up and down. So we here use this form to make the following analysis much easier. Okay, so before talking about the actual performance, we want to first talk about solution. So we want to figure out what is the solution if I give different type of input, like the step input, the ramp input, and the hyperbolic input. So what is the output as y sub t for a given second order system? Then we can talk about the performance. Okay, so before talking about the solution, we'll talk about so here the Wn typically is positive right over here. Wn is positive over here for the second order system. So this theta is also not less than 0. So here's what assumption we typically make, because if it's less than 0, if this theta is less than 0, now my s squared plus 2 theta Ws plus Wn squared can be written as, if this is negative, you can write this as s plus something times s plus something. You get real solutions. So they will go back to the first order system. You decouple as two first order system, right? So this won't be covered in this case. So here we talk about one theta is also non-negative. So which means we could have different cases for theta. So I divided theta into 4 different cases that I mentioned over here. If theta is 1, so we have s squared plus theta. You replace theta by 1, 2 Wns plus Wn squared, which is exactly s plus Wn squared. Okay. If theta is 0, apparently this middle term will be gone. So it's just s squared plus Wn squared. If theta is less than 0, but less than 1, but greater than or equal to 0, this one can be written as. So what we do is we make this one, we add on one term to make a square. Of course, there will be some minus the same term. So we sort of plus this term to make a square and a minus term. So then we have this one. Okay. If it's positive, greater than 1, we can do the same way. Okay, plus this one, but it becomes a minus. Okay, for this case. Okay. So what we do is, so basically what I want to do over here is so we want to talk about solution for different theta. Okay, so in particular, when theta is 1, we have critical damping. When theta is 0, we call it no damping, because this is called damping. This by the way, the theta is also called a damping factor. Okay, because this plays a role in the control system performance that I will talk about later on. So when theta is within 0 and 1, it's called under damping. When theta is greater than 1, it's called over damping. So those are also the control parameters sometimes we have to select to make sure if we want a critical damping, no damping, under damping, or over damping. Okay. Alright, so let's first start with the case when we have a UT input. The input u sub t is 1, which is a step. This is also called a step input. Okay, in other words, if we do the Laplace transform, the u sub s will be 1 over s. So you can use a table to look up why the Laplace transform of a step input is just 1 over s. Okay, so once we have that, we want to figure out, hey, for a step input, what is my output, y sub t? Okay, so let's try that out. Okay, the simple way we can compute it is using the Laplace transform, the inverse Laplace transform, as we mentioned at the very beginning of the class. So we have y sub s, which is u sub s times this the system, right, which is given by this form. Okay. Once we have that one, we just do the multiply by this, but we replace us by 1 over s, and when put them together, that's what we have. Okay. Let's use to make it a little bit. Okay, so that's what we have. So this one, according to the partial fraction expansion, we sort of can write this as, we split this one with that different, right? We split this as a over s plus bs plus c over s squared plus 2 theta ws plus wn squared. So that's what we have. Okay, now we have to figure out what is the a, what is b, and what is c, right? So we just have to replace this one. What we do is we assume this one should be equal to my original one right over here. So I multiply both sides by, so this guy right over here, this guy should be equal to this guy because I rewrite this y as this form, right? Which means if I multiply both this form and this form by this part, okay, I multiply both by s squared plus 2 theta ws plus wn squared. I also time the same thing as s squared plus 2 theta ws plus wn squared, and we do some simplification which becomes this guy. Okay, now this guy, we do the multiplication, this will cancel out this s, but the remaining term is this. So that's why we have a time this whole thing, and this guy is bs plus c, but this guy cancels out, so I have s over here, so s times bs plus c. So this guy, if you time this, will cancel out, you have wn squared directly. Alright, so once we do that, we can clear a little bit. So we just put all the coefficients for s squared, s and constant on the left hand side, which should be equal to the right hand side. You can also sort of consider right hand side as wn squared plus 0 times s squared plus 0 times s. So what we do is set those parameters as those coefficients to be equal. Like for s squared, coefficient for the left hand side is a plus b, right hand side 0. So we have a plus b 0, and then we have here is 2a theta wn plus c. This is my s, right? This also be equal to 0. We set it to be 0. And then we set last one is a is equal to this is, you can see this is a 1 time wn. So I have a is 1 from here. You can see that. And then a b plus c, a plus b is 0, so you can see b is negative 1. And then for here, I can also compute c is this. So essentially, after you do all the calculation, I can write a y sub s is 1 over s plus negative s negative 2 theta wn divided by s squared plus 2 theta ws plus wn squared. So that's what we have. Okay. Now, in order to find a solution, we just do the inverse Laplace transform. Okay. Fortunately, for the by using the linear property, it's just the inverse of 1 over s plus inverse a whole bunch of stuff over here. So this guy, if you look at this guy, so this is just use a table. The 1 over s is inverse is just 1. Okay. Right over here, this is y sub t is equal to L inverse of y sub s. And the difficult part is this side, this part, because this is very hard to quantify. This one you can tell it's just constant numbers, it doesn't change. This is something we quantify the control performance. Okay, so the key part is how do we analyze what is the inverse of this whole bunch of this complicated stuff. Okay. Alright, so in order to do that, we analyze the inverse of this complicated stuff according to different theta values. It's called over damping. This is critical damping. This is no damping. This is the under damping. This is over damping. Okay. We start with a very simple one when theta is 0. Okay, make it a little bit simple to see what's happening. If I have that one, okay, once you have the theta 0, we just replace theta by 0 over here. So what I have is, so this part will be gone. So I have the numerator will be the same. Denominator become s squared plus wn squared because theta is 0. So this one, well, I can write this one because also here, I forgot about this is theta because the theta is 0 here. This also is gone. Okay, so I only have negative s over s squared plus wn squared. Okay, so I have, because this is 0, like I said, this is gone. This is 0. So I have only negative L, negative. I can put L inverse of negative s. I can put negatives outside. It's a negative L inverse s divided by s squared plus wn squared. If you do that one, if you look at the table, what you find is just negative cosine WNT. Okay, what to do that, if I draw the output, this is input-output relationship. So you sort of have like input-output like this. So I should draw a little bit clear this because this is a negative cosine WNT, I believe. Okay, is negative cosine is going. So it's sort of like this. I will draw this. It's going opposite. And also its magnitude is 1. So it's gonna reach that one. So you sort of have, this is my y sub t, okay? So it's a sinusoidal function, and hold on, see. Okay, I think I draw this one. Previous one is correct. Okay, I should draw this, redraw this one as, okay, this. Okay, this is y sub t. This is my y sub t. The reason, because I just draw negative cosine w and t, because yt is a 1 minus this one, so you have, this is my y sub t. So the y sub t actually is a sinusoidal function, so that's no, you sort of can see there's no, it doesn't reach the u sub t, okay? It just keep going up and down without any, it's no steady state, okay? Now let's move to the second case when theta is 1, which is a critical damping. So when you have critical damping, we have theta is 1, so which means I can replace theta by 1. So if the numerator becomes negative s plus 2wn, and denominator becomes s squared plus 2, this is wn, because I replace theta by 1, plus wn squared. So this is L inverse of negative s plus 2wn divided by s plus wn squared, because this I can write this as a square form. So this one, according to what we learned for the partial fraction expansion, this guy can be written as, we only look at this over here, this one can be written as a over s plus wn plus b divided by s plus wn squared. This is by using the partial fraction expansion, because this is a repeated real and repeated poles. Okay, so in order to figure out n and b, we multiply both sides by s plus wn squared. Okay, so we keep on doing the simplification, do the calculation. So what we figure out here is a is negative 1, b is negative wn. Okay, so once we do that, we write this negative s minus 2wn divided by s plus wn squared, which is what we computed right up here. Is we replace this a by negative 1, b by negative wn. So it's negative 1 plus s plus wn plus negative wn divided by s plus wn squared. Okay, once we do the inverse Laplace transform, we have L inverse by using linear properties, linear L inverse this guy plus L inverse this guy. Okay, so once we use a table, we figure out this is a negative 1 times e minus wnt times e minus wnt. So that's what we have. Okay, so accordingly my yt is just 1. Don't forget about the 1 plus L inverse of this whole thing, right? So this is equal to 1 minus, we replace L, this stuff is, this is given by over here, so we replace this by whatever value we compute over here. This is 1 minus e minus wnt plus minus wnt e minus wnt. So what do we have somehow over here? So when we have ut is output sort of like this. Okay. So by moving on, when we have, this is called under-damping case. Okay, under-damping. So again, the form will be the same. Okay, the only difference is the theta now is between 0 and 1. So once we have that one, we sort of rewrite this a little bit as we mentioned at the very beginning, right over here. Write this form. Okay, when it's under-damping. Okay, let's go take a look at what's happening. So we write this as I mentioned before. So it's something like this. So what happened is I have 1 plus L inverse of this guy over here and this guy over here. Okay, so what's happening is I sort of here, this is, you have a sinusoidal function over here. Okay, I'm gonna spend a little time to figure out, I'll tell you how I do that. What we basically say we can consider here, this is somehow, we write this form here because I know s plus a squared plus b squared. This is s plus a. Now, if I do L inverse this guy, this is appearing in the table, okay? Or if it's L inverse of b over s plus a squared plus b squared. You can also have something like this. This is something you can figure out basically, right? So that's why we want to have sort of, we want to rewrite it sort of in this form. You could have a linear combination of these two, it's okay, right? So we keep this denominator to be the same. Okay, you sort of consider this is a, theta type W is a, and the square root of 1 minus theta squared type W, and this is a B. Okay, this is my B. Okay, this is W. Sorry, you can see it's W. This is W, and it's W. Okay, that's okay. And then, of course, on the numerator, we sort of want to S plus A. We want to have same value, right? So we just write this S plus theta Wn. Okay, and then the here part remaining. Once you do that, remaining part will be theta W minus 2 theta Wn. Basically, okay. So once we do that, we sort of can write this as, first one is here, second one is a plus L inverse of negative theta square root of 1, because I want to have this form. Basically, I want to have this the same one, right? So I can divide it, but also time it, so you get this one figure out right. Okay. So by doing that, I can move this one constant to the right hand. The reason I want to do that because I want this guy, the remaining part over here for the numerator here, and this guy, they are the same, right? They're the same. Okay. So once we do that, we sort of have the E. This guy is standard form. So this is this part. You only, if you consider this A is W, and we basically have S plus A over S plus A squared plus W squared. You can use a table to figure out what is the inverse. Okay, the inverse is just given by 1 e to the negative AT times cosine WNT. That's what's the inverse of that. The inverse Laplace transform. That's this form. For this one, if I pull this one outside, okay, and the inside will become this W divided by the S plus A squared plus W squared. If you do the sort of consider A is this and W is this, okay. So once you do that, the inverse is not a complicated figure out. It's just negative AT times sine WT, right? Okay, so once you do that, of course, don't forget about you have to scale this one by some number. You can copy that one. So this is the solution of this complicated stuff, okay? So don't forget, we also have a 1 over here. So it's a 1 minus stuff and minus stuff. That's what we have. So if we draw the actual output, so this red one is my U sub t, and my blue line is the Y sub t. You sort of can see is something like that. It's the sum overshoot, and then you will stabilize across the value of 1, because this is 1. You stabilize 1. Okay. Okay. So what if we have theta is greater than 1? So this is called over damping. Okay. So if you do that one, so basically what we do, we want to rewrite. So the output is still Y sub t is still by 1 plus is L inverse the whole thing, right? So this one, you sort of can write this as I mentioned before, is S plus S1 or S minus S1, whatever, time S minus S2. This one basically says the poles, if you have theta is positive, the poles are real and distinct. So which means, yeah, you can sort of rewrite this one as two forms, right? This is real and distinct, right? And the only problem I have to figure out is what is my S1, S2. So essentially, you can figure out S1. Okay, I don't want to go into detail about how to compute that. You actually just the S1 is negative theta Wn minus square root of theta squared minus 1 times Wn, and S2 is negative theta Wn plus square root of the theta squared minus 1 Wn. So those are all negative. These are all negative, and also S1 is not equal to S2 because this part, if you look at the value, so this part they are equal, but this one definitely you plus and minus something. So this also equal. If you don't look at the plus and minus sign, because you plus and minus definitely they're different. Okay, so that S1 is not equal to S2. So by doing that, so what we can do is I can sort of write it as YT is 1 plus L inverse A over S minus 1 plus B over S minus S2. Okay, so the solution will be 1 plus A ES1T plus BES2T. So remember, note here, this is the S1, this is negative, and this is also negative, and also the real. So you gotta sort of overdamping because it's going to take a lot of time for you to move from this YT, go from 0 to 1, because eventually this negative, the limit of this guy will be 0. Limit of this guy will be 0. So this will be gone. So limit is still 1, but it takes more time to go to that point. Okay. So here's a brief summary talking about how do I compute the y-st for second order system. So for the, if I have a step in, I just talk about step input, so it's easy to compute. But actually for the, if I have t, the ramp input and also hyperbolic input, this become more complex, okay? So summarize for the use of t when it's the step input. So for theta is 0, this is a critical damping. So the solution is sort of, I will probably redraw it, is somehow like this. It's a sinusoidal, okay? So without no steady state. And also there's no steady state error because the limit of y of t minus u of t, okay, as t go to infinity. This one for this guy does not exist. Does not exist. I mean for this case. Okay, it doesn't exist, so there's no steady state error. For under-damping, when theta is between 0 and 1, under-damping, so okay, here's the pose of the location, the pose for the transfer function, okay, because they are on the real axis. When theta is within 0 and 1, we have two poles, they are complex conjugate, and real part is on the left hand of the imaginary axis. So the actual output here is also oscillation, but is a oscillating, but the final value will approach the use of t. So you can sort of see the limit of y(t) minus use of t will, as t goes to infinity, will be 0. Okay, so when we have theta is 1, this is called critical damping. So we have repeated poles on the real axis. But of course the poles have negative real parts. Okay, so what happens? We have the poles of the system response will be somehow like this. Okay, so again, this is red line represents the use of t, okay, and this is one, this y of t is my blue line represents y of t. So the y of t also will approach the use of t, so the steady state error will be also 0. When we have theta is positive, which is greater than 1, we have critical and over damping. So it just takes a little bit longer time for the y to approach the steady state, which is 1, but the error is still 1. So for if we do the summaries, if you look at the summary for the computing y of t for a second order system given a step input, use of t which is 1, so only for either for under-damping, critical damping, under-damping, critical damping, and over-damping, the steady state error will be 0, which means the output and the input will be the same eventually. However, for no damping case, there's no steady state error, and also the output will be always sinusoidal. There's no steady state. Okay. So here I want to talk about when we have, you can sort of imagine, okay, when we have use of t is t, of course, if you do the Laplace transform, so use of s will be 1 over s squared. So the system will be more complex. It wouldn't we wouldn't have a very good solution. We can also find a solution, of course, but the solution will be much more complicated. Okay, you can follow the same concept to understand what is the final state, what is the final value of yt looks like. Okay. So I wouldn't talk about this too much, and we couldn't see a lot of this transient performance for this type of inputs. That's why we'll focus on when we have use of t is 1. It was a step input. We can find the transient response much easier. In particular, in a lot of real-world applications, our goal is not to drive my output to certain increasing value. Typically, we have ut to some steady state. For example, when we drive a car to certain speed, typically we want my y of t to approach some constant value per se as t go to infinity, rather than I want to have yt to go to some function. This is rarely the case. Or you can also think about this, if it would even go to some cis of t, right? I can say I want my goal to yt minus cis of t is equal to 0. You can also do a change your system dynamics by looking at y of t minus cis of t rather than just y of t. Okay, so typically look at it as a y equal to a constant. Okay, so this lecture only focus on the how to find a solution. Okay, solution to the for a second order system by given input u of t, which is given by 1, the step input. We haven't talked about transient performance response yet. So in the next video, I'll talk about how do we define the transient response, or what kind of metrics we're using to quantify the transient performance.